Alright, so today is the first lesson in your video lectures. Well, there are other video lectures floating around, so maybe not for everyone, but this is my first time doing this on my tablet, I suppose. So we're going to talk about scapegoat trees, and because of the craziness of this last little while, I'm going to back up and review everything, and that way it's a nice complete lecture as well. Hopefully everybody got the email about the new structure of the course, so you're all familiar with it. The test 2 was moved back, and it's now, there's I suppose sort of a floating deadline, so you start it, but once you start it you must complete it, and then I forget what I set it to, but I think I should give you back the marks right away. I just don't want to give feedback because I want to keep sort of the answers a mystery. And your exam will take the same format. It's sort of a floating deadline. So you start it when you're ready, and then you do it in one sitting, and then you're done. But okay, so let's talk about scapegoat trees. This will be the second time I do the intro because I'm just getting used to this audio-visual stuff, and I'm having to learn a lot. So my apologies for any mistakes I make along the way, bad cuts, bad audio, things like that. So what is a scapegoat tree? Well, so we've looked at binary search trees. These implement sorted set interface. Which means add x, remove x, and find x. And all of these operations on a binary search tree are O of the height of the tree. So what is the height of a tree? Well, we could see a couple different cases, I suppose. One example might be this. It sort of becomes a list instead of a tree. So this is the worst case. And this is O of n time now, because the height of the tree is equal to all of the, it's on order of all of the items. In our best case, we have something that's quite well balanced. And then the height of the tree is, of course, logarithmic in this case. And we get this O of log n time, which is much, much better than O of n. So that's the power of these if we want to balance a binary search tree. And so how do we ensure that they're balanced? So how? We have a couple different strategies for that. Randomization is one. It works pretty good. At some point I might show you a random binary search tree, probably when we get to that section. Rotations. So we might see that red-black trees. And rebuilding. And rebuilding is the one we're going to look at today. So okay, so then how do we rebuild our balanced binary, or our binary search tree? Yeah, so how do we rebuild? There are many different strategies, but we will use one in particular. So we gather the nodes of the subtree into a sorted collection. I'm going to say collection here. In the textbook, they use an array. I'm going to use a collection just because I think it makes the presentation of it easier. And they're not that different. You just don't have to be as careful with your indexes and things when you use a collection. A lot of that, those details are abstracted away nicely. So I think it's easier to present the algorithm just using sort of the abstract collection class or list class. And then once we've gathered all those nodes into a sorted collection, we use this collection to build a balanced binary search tree. And we want it perfectly balanced. And by perfectly, perfectly balanced, by perfectly we mean that the depth of any two leaf nodes differs by at most 1. So depth. So as perfectly as we can. Okay. So then here we have an example of, and I'm just going to add in one node here. The reason being, this would be I want it sort of be a relevant example. So if we add a node here, then this is a scapegoat tree that requires rebuilding. So how do we rebuild this? Well, we do a traversal of the subtree we want to rebuild. So let's see, we want to rebuild the subtree rooted at 5. So we collect all these nodes into a sorted collection. So we do that by doing a traversal. Now, if you recall traversal, we're going to, there's a recursive version and a non-recursive version, an iterative version. We're going to use the recursive version just because the logic is much more clear, but they are functionally equivalent, except for the recursive version can crash if you don't use, because it does put everything on the stack, so it can overflow the stack. But so traverse u.left. So we, and the nice thing about these recursive methods is that they, the base case, they bottom out elegantly, especially with these nil nodes. So this is sort of the traversal that we're going to use, but this is an example of a depth first search. And basically, if we start at 5, or let's use a different color. Let's use blue. So we start at 5, and the traversal visits them in a depth first search fashion. So it goes down all the left children first, explores them, and then comes back up and explores the right children if they exist, and then back up to where we started. So that's the traversal, and we have, of course, a pre-order, an in-order, and a post-order traversal, and we want to do the in-order traversal in order to collect the nodes in sorted order. So in in-order traversal, we process the node in between the left and the right subtree. So if you want to look at that visually, it would look like, well, we start at 5, we go to 2, we go to 1, we go to 0, and then finally we start processing. So you can kind of think of it as, you know, if we draw this little blue path, then we process when the blue path goes underneath our node. Okay, so then 0, 1, 2, and then it goes down to 4 in the right subtree, 3, 2.5, and then it processes that. It processes 3, it processes 4, and finally it processes 5. So that's the in-order traversal, and that gives you everything back in order if it maintains the binary search tree property. And just to briefly review, we can do a pre-order traversal, which is, if you want to think of it, where it's when our path passes to the left of our node. So the first time it sees the node, it processes it. So that's the pre-order traversal. And then, of course, the post-order traversal. So if we use blue again here, it's when our path passes to the right of a node. So post-order means I do, we'll put it here, post-order. So after I traverse my left subtree, my right subtree, then I process my node. So here, 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 here. And it's when our path passes to the right of our node, so to speak. Okay, so those are all the traversals, but the one we're interested in is the in-order traversal. So this guy here. And that's going to give us back the all of these nodes in sorted order. Okay. And then we used, once we have them in our collection in sorted order, so here we would just call, we would pass in some list and say a.add u. All right, so if our list was called A, we passed in a list of type node here as an argument, then calling a.add u here would return a sorted list. Okay, and then we want another. We want to take that sorted list and we want to build a balanced subtree. And again, this is not quite in the textbook. They use the array. I'm going to use the list, sort of a collection member, because it's slightly more elegant. If a.size equals 0, then we're going to return nil. So this is so we want this to return the root of this balanced subtree. Okay. And then we want to grab the center index. So that is a.size over 2. We want to grab our root node of this particular subtree. So root equals a.get center. And then we want root.left equals our recursive call of build balanced. And we could just use the sublist method. So the sublist is 0 inclusive, and this number is not inclusive. So this is actually the sublist from 0 to center minus 1. Okay, so you guys might notice, I don't know, there might be a different sound quality or whatever. I had to switch recording software because the other one was apparently a trial version. Anyway, so through the magic of video editing, I've completed this root.write as well. So this is basically the recursive structure of this build balanced method that we're looking for. And here we go from center plus 1. So we can see here center plus 1 to a.size. So center plus 1 inclusive, a.size not inclusive. And it might so happen that they're the same number, in which case that would just return an empty list. Okay, so that's basically the structure of build balanced. Once we've done that, we can return the root. However, we also have to, if something was returned that's sensible, so if root.left is not nil, so it could have returned a nil node, it could have been empty. But if not, then we want to set the parent pointer, right? So root dot left dot parent equals root, and we would do the same thing here. So set parent pointer, and that is basically more or less. This is how you build a balanced subtree using an ordered collection, and this sort of a little piece of code will likely come in handy for assignment 4. This piece or the piece from the textbook. Just as long as you understand how it works, the mechanics behind it, then you'll be fine. All right, so then so we've seen the basics of rebuilding. So now let's look at scapegoat trees and how they use this rebuilding to maintain a balanced binary search tree and give us that logarithmic search time and add and remove that we'd like. So yeah, it's a subclass of binary search tree, and it employs the philosophy of when something goes wrong, like there's a global pandemic, then you look for a scapegoat, and then once you find the scapegoat, you make them take care of the problem, and that solves everything. So yeah, so what it does is it maintains the binary search tree property. That means everything in the left subtree is less than or equal to the root, and everything in the right subtree is greater than or equal to the root. And if we're dealing with the set interface, then it's not less than or equal to or greater than or equal to, it's actually less than or greater than. So let me just write that out. In left subtree of node U are less than U dot X, and all items in right subtree are greater than U dot X. And greater than or equal to if you want to be a little more flexible about that set property. But, and it maintains logarithmic height through rebuilding. And we've seen how to rebuild. Now we're going to see when and I guess why. So let's look at the structure of our scapegoat trees. So it maintains we'll do a little pseudo class definition just to define a few things. So we maintain n, which is the number of items. And we maintain q, which is an overestimate of n. And we'll see how that comes into play when we do our rebuilding. So what we want to maintain is a few things. We maintain that q over 2 is at least, or is at most n, and that is at most q. So q is the upper bound on n, but it's never less than half of n. And we maintain that the height of our tree is never more than So log base 3/2 of q. And that maintains, that gives us a logarithmic height on the tree because, well, that's at most log 3/2 of 2n because of this bound here. And then that is equal to log 3/2 of n plus log 3/2 of 2, which is less than log 3/2 of n plus 2. All right, so then by maintaining this height here, we get a logarithmic bound on the height of our tree with respect to the number of nodes it contains. But even given all that, it can still look very unbalanced. So we'll see an example here. I just get my, let's see. Okay, so it can still look unbalanced. So here's an example of a scapegoat tree that still doesn't look very balanced, but it's still balanced enough. It has a logarithmic height and it still gives good performance. All right. So let me move that out of the way for a second. So now we're going to implement the sorted set interface. So we have find x, add x, and remove x. Find x, we use the same algorithm as a binary search tree. Oops. Except now, since we have a guaranteed logarithmic height, this takes O of log n in runtime. For add, so let's just get that out of the way for a minute. Okay, so add's going to be a little bit different now. So when we call add, we increment n and q. And then we add in the same way, but we keep track of the height or the depth. Depth because so if we think about it, then the depth of the deepest node is equal to the height of the tree. So when we keep track of the depth and making sure that it doesn't violate our bound, we're really making sure that the height of the tree doesn't violate that bound. Okay. So we search for x, then add a leaf with that contains the data. So we set u.x equal to x, and we keep track of depth of u. And then, so if the depth of u is less than or equal to log 3/2 of q, then our tree is still balanced. So we do nothing. So then our add operation was successful and we can return and everything's great. So what happens if we violate that bound then? then we have to rebuild. So let's go through an example then and see exactly how this works, and then we'll go through the details. So let's say we want to add 2.5 to the scapegoat tree. So what we're going to do is we're going to search for it. So 2.5, we start here, it's less than 7, so we go left into the left subtree, it's less than 6, we go left again. Here it's greater than 2, so we go right, and here it's less than 4 and less than 3, so we're going to add it right here. So this is the example we saw before. And we keep track of the depth of this new node. So this is our node U now. And the depth of U is equal to, well, if we go back over it, we start at 7. It's the number of steps we took downwards. So from 7 to 6 is 1, 2, 3, 4, 5, 6. So depth of U is equal to 6. And we'll say that our Q is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So Q happens to be equal to N in this case. Let's say it could be greater, but in this case we're going to say that it's equal to it. So then we look at log 3/2 of Q equals log 3/2 of 11, which is about 5.91. So what that means is the new height of our tree is 6, and that is higher than log 3/2 of Q, which means we violated our height restriction. So that means, therefore, we must rebuild part of the tree. And in particular, we have to find a scapegoat where we're going to rebuild. And so we're going to find the scapegoat. W, which is a node. It's an unbalanced node. So it's a node where the size of the child of W, one of the children, over the size of W itself is greater than 2/3. All right, so that's the guy we're looking for, is the W that matches this description. So we're going to start at 2.5 at our node U and walk our way up the tree until we find a scapegoat. Okay. So then we're first going to check the parent of 2.5, so that's 3. And the size of 3 is 2, so it's 3 and 2.5. So that's our size.w is 2. And the size of just the 2.5 node is 1. So that's 1/2, and that is still less than 2/3, so we're okay. So we move up to the parent of 3 now, so we're up at 4. The size of 4 is 3, and the size of 3 is 2, and that is exactly equal to 2/3, but not greater. So we're looking for greater. So that guy's okay. So we go up to 2, the size of 2 is 6, and the size of the child of 2, which is 4 in this particular case, is 3, so that's 3/6, and that is still less than 2/3. So we climb up again, we look at the parent of 2, which is 5, the size of 5 is 7, and the size of the subtree, 2 in this case, is 6, and that is greater than 2/3. So we found our scapegoat. Our scapegoat is 5. Okay, so we found our scapegoat. We're going to rebuild the tree at 5. So let's sort of copy that down. So 7, 6, 8, 9. rebuilding the subtree that's rooted at 5, the scapegoat. So we're first going to gather all of those into a sorted collection. So it'd be 1, 2, 3, 4. Actually, I have 2.5 in there. 2.5, 3, 4, and 5. So if we have this sorted collection, and then we're going to take the middle element of that, which is going to be 3 in this case. So you can take 2.5 or 3. I believe the code works out to 3 just by the way it rounds, but we're not really concerned about which side you make larger or smaller. Actually, let's keep that separate for a second. So 3, and then 4 and 5, we recurse on the right hand side and on the left hand side. So over here we get 2, 1, and 2.5. And over here we get, again, if we, depending on how this math works out in the code, we would get something like this. So this is a call to rebuild. And we will look at the code or the pseudocode for that. So we're rebuilding at 5, and now it returns the root of the tree, which is 3. and then we have to reattach it to the tree. So we have to keep track of the parent and insert it like this. So this is our rebuilt scapegoat tree. And yeah, so we'll see how all that works out in the code in the next part. And all right, we have, so we're going to look at this basic structure of the code, nothing too deep. So we have seen pack into, what did I call it, collection maybe? In the book, it's pack into array. The pack into a collection is just arguably a little more elegant. So we use a list of node. Okay. We've seen build balanced. This returns a node. This is a void. So I'm not going to go over the code for these again, but we are going to use them. This is our list node A, and that's sufficient. So now, so one of the things that we do frequently is rebuild. So to do that on our scapegoat tree, again, I'm going to go over some sort of high-level details. So the first thing we want to do is we want to keep track of the parent. So when we rebuild this part of the subtree, we may get back a different node than u, and we need to know u's parent so that we can link it back into the tree. So u.parent. And then we want to say make a new list. And then, so pack into array, or pack into collection. That will store everything in this array. So pack into collection, and we'll pass it u and a, and then node new tree equals build balanced. All right, so that returns a new tree. So now we want to hook the new tree in with the parent p. So it's just basically check which child. p node u is, and replace it with new tree. And you have to check all the same edge conditions, if it's the root, if it's a nil, etc. Okay, so that's the basic rebuild algorithm. This, of course, I'm way overly simplifying, but it's a lot of tedious edge cases, if else. All right, so then the next thing we want to look at is our add function. So we discussed that find is the same as a binary search tree, but now our add function is, and we'll look at the runtime of this build balance when we do the analysis, which is the next step. Yeah, so we put this in a node. And then, so we discussed this method. I'm not going to go over it. It's add with the depth, and it's basically, you should be able to write it. It's basically an add function that just keeps track of every time you step down into the tree, so that it returns the depth of the node once you've added it. And then we want to check. Now this is actually, so I've written it here as a math equation, but log 3/2 q is actually a method. So in this case, depth is exceeded, find scapegoat. So node w equals u dot parent. Okay, so now we're walking up from u, and while 3 times size w, and this is a size method. I believe we talked about it briefly. So we can compute the size instead of storing the size explicitly. So this is a method where we pass in the node that we want the size of, rather than you know, in a normal collection where you just call the size method for that collection. So it's just slightly different. But while we haven't found the scapegoat, w equals w dot parent. And then, once this while loop bumps us out, we found the scapegoat, so we're going to rebuild w.parent. And then return d greater than or equal to 0. That just means that's one way to check that we've actually added something. And we did, if d is less than 0, then the add with depth is going to return -1. Add with depth failed, basically. Okay, so that's the add function. Basically, find the scapegoat, rebuild, and remove is so all of these, the search paths are O of the height of the tree. It's just the rebuild function, basically, we want to look at. So if super.remove, So if our remove was successful, now what we're going to do with remove is we're going to check if we're going to check our lower bound on Q. So if n becomes too small, then what we're going to do is we're going to rebuild the entire tree. Okay, and then we'll prove that in the next section that we can amortize it the same way we've proven so often in the past. So if if n is less than half of q, basically, then we're going to rebuild the entire tree at the root. And then we set q equal to n. And return true. And otherwise return false. That's just keeping with the specification of the remove function. Okay, that's it. So ignoring the cost of rebuilding, the runtime of this is O of log n, because it's O of the height of the tree. And also the add method, although we didn't talk about it, well, we'll talk about it right now. So the depth, add with depth is O of log n, because all it does is it's simple, the add function with a counter. So that's the log n, it's O of the depth of or height of the tree. And then this part here, if we have to climb up and find the scapegoat, well, we're at most going to go through O of the height of the tree again, so this is also O of log n in terms of runtime. Because we can only climb from the leaf to the root, so it's the O of the height of the tree. So excluding calls to rebuild, all of these methods take O of log n, if you believe me that we can keep our tree properly balanced, and we're going to show you that in the next section. Okay, so now we're going to look at the analysis and correctness. We're going to start with proving that a scapegoat exists. So we're going to show if we violate the depth bound. So the claim is that we violate the depth bound, then we can go up the tree and find a scapegoat and then rebuild it that scapegoat. So we want to prove that if we violate the depth bound, then we can always find a scapegoat. So we'll prove that in a lemma. Let U be a node. Of depth. So we'll say it's the deepest node, so therefore the depth is equal to the height of the tree, and that is greater than log base 3 halves to the q, which is what we check for before we rebuild. Then there exists a node W on the path from U to the root such that it's an unbalanced node. In other words, size of W over size of W dot parent is greater than 2/3. All right, so we're going to prove that by contradiction. So proof by contradiction. So then we're going to assume that there's no such unbalanced node, and therefore that every node W on the path from U to the root So for each of them, that the size of W over the size of their parent is at most 2/3. And we will show that that leads to a contradiction. And what we're going to show is that it would imply that the tree has a size greater than n. Okay, so how are we going to show that? Well, we know that the node that we added is u, and we know the size of u, since it's a leaf, is 1. Okay, so now we're going to take this and make it into sort of a, we're going to flip it around and make it into a growth function. So this is sort of logically equivalent to if size of w dot parent over size of w is at least 3/2. Right? So every step I take up in the tree, that my parent is at least 3/2. You know, in a sense, it's greater than me, right? So it's at least 1.5 times bigger than I am. Okay, so then given this growth function, we would know, for instance, that size of u dot parent over size of u is at least 3/2. Okay, so that's, and I mean, that's nothing spectacular. We know size of u is 1. The parent is going to be a size of at least 2, so of course it holds in this case, but it's going to hold all the way up the tree. And in particular, we could say that size, for instance, to take another specific instance, size of u dot parent over size of u, which remember is equal to 1, is at least 3/2 squared. So then if we generalize this all the way up to the root, so to go up to the root, we are going to take h steps. So then the size of root over size of u is at least 3/2 h. Right? And since size of u is 1, this is basically just the size of the root, size of the tree. Okay, and we know that h is greater than log base 3 over 2 of q, because that's what triggered our rebuild. And we know that this is at least log base 3 over 2 of n. So we could say that h is greater than or equal to log 3/2 of n plus 1. Since it's a discrete number and it's definitely greater than log base 3/2 of n, so it must be at least log base 3/2 of n plus 1. Okay, so then we can compute the size of the root. Is 3/2, or is at least 3/2 log 3/2 of n plus 1, which is equal to 3/2 log 3/2 of n times 3/2. So 3/2 to the log base 3/2 of n is equal to n. So then the size of the root is n times 3/2, which is greater than n, which is therefore a contradiction. So if we don't see any imbalanced node, that implies that our tree is at least 3/2 the size that it's supposed to be. All right, so that's our proof that we can indeed find a scapegoat. All right, so next we're going to show that if on a call to add, if we have to rebuild, that the cost of finding the scapegoat and rebuilding is proportional to the size of the subtree that we're rebuilding. Right, so then we have lemma 2. So during a call to add, the cost of finding a scapegoat. Which we'll call W, and rebuilding at W is is O of the size of the subtree rooted at W. Okay, so so the proof of that is as follows. So the rebuilding is clearly O of size of W. All right, so we do an in-order traversal. We collect all the nodes, and then we build the tree. We see each node a constant number of times. So it's O of the size of that subtree. So what's left to prove is that all the calls to size, where we have to sort of compute the size of these subtrees on the fly, is at most on order of the size of the subtree rooted at W. Okay. So let U equals U0, U1 up to UK equal W. So U is the node we added, and W is, of course, the scapegoat. And B, all the paths on the node, all the nodes on the path from U to W. So we effectively call size on each of these nodes. However, since W is the first unbalanced node on that path, otherwise the first unbalanced node is the scapegoat. So since W is the first unbalanced node on that path, then we know that all of the rest had to have been balanced. So we know that size of UI over size UI plus 1 had to be at most 2/3, and that is for 0 less than or equal to I less than or equal to K minus 2. Okay, so therefore we can compute all the calls to size, so therefore the cost and I mean, hopefully at this point you can sort of tell that this is a geometric series that starting from the size of W, it decreases at least a geometric rate, if not more. But that's essentially the argument, except we're going to do it in math. So it's 0, big O of I equals 0 to K, and the size of U of K minus I. And we're in a sense counting backwards because we want to start with size W and we want to apply some constant fraction all the way down to U. So that is equal to big O of the size of U of K, which is W, plus 0 to K minus 1, K minus I minus 1. Okay, and then of u. Okay, so now if we count, in a sense, now we're counting backwards from the size of w, and applying this this geometric bound on it. Which is O of size (1 plus I equals 0 to k minus 1, 2/3). And since 2/3 is a constant fraction, this is a geometrically decreasing sequence, so it gives us some constant times the size of uk, which is the size of w, which is what we want. So all the time spent in the calls to size is at most O of the size of our scapegoat. So now we are left to prove, we're left to bound the cost of all the time spent in the rebuild operation. And our claim is that, well, let's write it down. So we're going to bound the time spent in rebuild, lemma 3. So starting with an empty scapegoat tree, any sequence of m add or remove operations, results in at most O of m log m time in rebuild. Okay, so to prove this, we're going to use a credit scheme. So credit is another way to keep track of, similar to the potential function. It's just another way to keep track of these these functions that sort of fluctuate, and they're difficult to track by themselves, but when you sort of define them relative to something else, then it becomes easier. So we use this credit scheme. During insertion or deletion, we give 1 credit to every node visited on the path. To every node visited. So since we started with an empty scapegoat tree, we've given out at most the height of the tree per operation, and that's at most since we've started with an empty tree and we've done m operations, that means we have at most m items in there, or that is q is at most m. Right. During a deletion, we store an extra credit on the side. Okay, so thus m calls, we give out at most m log m credits. so now we want to show that this is enough to pay for all of our calls to rebuild. Okay. So now we call rebuild U or let's say rebuild W, since that's traditionally our scapegoat. On a scapegoat W. And without loss of generality, let's say that size of W dot left over size of W is greater than 2/3. Okay, and we know that size of W is equal to 1 plus size of W dot left plus size of W dot right. Therefore, 3/2. So if we take this, this here is equivalent to saying that size of W dot um, 3/2 of size. So if we move the 2/3 over to the left-hand side of the equation and size W over to the right-hand side, we get that the size of W dot left is at least 3/2, or 3/2 times the size of W dot left is at least the size of W. So then we get greater than 1 plus size W dot left plus size W dot right. So we've just substituted this in for the size of W. So we can conclude that it's greater than twice the size of W dot right. Yeah, I just wanted to double check that for a second. So essentially we subtracted this guy from both sides, and then let's make this 100% clear. So we do one, or at least try and make it more clear. 1 plus size of W dot right. So if we multiply both sides by 2 and just subtract this this term here, this is at least twice size of W dot right. Okay, thus size W dot left minus size W dot right greater than 1/2 size w dot left, which is greater than 1/3 size of w. And that goes back to here. I divide, or I multiply both sides by 1/3 here, and that gives me this inequality. Okay, so size, so that means the, right. Last time a subtree with U was rebuilt. We had built something that was balanced, and that means that, or if it was never rebuilt, size of U dot left minus size of U dot right was at most 1. Okay, so the difference in them was at most 1, and that means we've had at least 1/3 size, sorry, U should be W. Minus 1 add or remove operations had to occur since then. Which is O of size of W. All right, which is what we wanted. So yeah, the number of add or remove operations was proportional to the size of the scapegoat. All right. And that gives us the so that gives us the M, in a sense, M operations, and then the log n time spent is the time spent traversing up and down the tree. So M is the number of operations, and the log M is the time spent in going up and down the tree. All right, so if we rebuild on a call to remove, then we know that Q is greater than 2n, which means that we have Q minus n, which is greater than n credits stored on the side. So that means, at least n deletions have occurred. From the last rebuild, which was when Q was equal to n. So that's the proof. So then to sum things up, a scapegoat tree implement the sorted set interface. It supports add, find, and remove in O of log n time per operation. Furthermore, beginning with an empty scapegoat tree, any sequence of m calls to add or remove results in at most O of m log m time spent in rebuild. And all right, that's it for your scapegoat trees.